certain reason, right? So if I want high electron mobility transistors, why would I use gallium nitride, right? So this sort of correlation, if we can make to start with, then if we have a new, if we want to design a material for some new function, right?
Sure.
So for tomorrow, I want a material which is, let's say,
Piezoelectric.
optically, yeah,
Piezoelectric.
piezoelectric. Let's take the example of piezoelectric. Piezoelectric, but has a large coefficient of piezoelectricity, and it should be stable over long temperature ranges, right? So those are my design constraints.
Yes,
How
sir.
do I go about, picking the material of my choice, or not even picking? Can I actually make something that, so this is where the engineering comes, right?
So
So
basically,
traditionally, it's all, yeah,
basically getting into the application from design to getting into
right.
something which is application, Professor. I get
Exactly.
it, Professor.
So initially, I mean, so we were looking at, okay, so typically, f- if I want a material which is piezoelectric, there is no point looking at materials which are centrosymmetric, right?
Yes, sir,
So
Professor.
first we have to understand that aspect, right? So if so we start at the basics where we say there's something that structure does, structure and symmetry. This material should have so and so symmetry. Okay.
Hmm.
If the material itself doesn't have symmetry, I will do something to the material to induce that symmetry or remove some symmetries, right? So that's why we took a huge dive into symmetry, and we spent a lot of time on symmetry to start with. Okay.
Hmm.
Then symmetry will tell me, whether the material has piezoelectricity or doesn't have piezoelectricity, right? So whether the features in the material that I'm engineering, right, so
Hmm.
have piezoelectricity or not, right?
So
So
basically,
it's either as,
tensor
yeah,
type properties you're looking at, Professor, something like that?
exactly. So it's a tensor property, and then, so if I have centrosymmetry, this tensor property is going to be zero. So there is no point in, saying that I can have electromechanical, so energy that transforms from electrical to mechanical domain.
Hmm.
That's transduction by using centrosymmetric materials. I should really look at non-centrosymmetric materials, right?
Yes, Professor.
But which non-centrosymmetric material? I have aluminum nitride, I have gallium nitride. All these are different sort of non-centrosymmetric materials. And
Hmm.
I have something like PZT, which is another non-centrosymmetric material, right?
Yes, sir.
So so the symmetry tells me a certain thing. Symmetry tells me all aluminum nitride, gallium nitride, the PZT, everything will have a piezoelectric effect, right?
Hmm.
But then my question then is, okay, but I want to use it to make a microphone, for example, right?
Yes,
And
Professor.
microphone would require me to have a large piezoelectric transduction, right? So if I apply small stress, I need large charges.
Hmm.
Or if I apply small field, I need large strain in this material.
So,
Okay.
Professor, so you're telling now you're going into thermodynamics, stack mechanics to get to understand.
Right. So the second part, which is thermodynamics and statmech, tells me that, it's not just about saying this material has this property or doesn't have the property, but
Yeah.
it is also about saying this material has this property and it is of this magnitude, right?
Hmm.
Or in some sense, a hand waving way of telling, or so some systematic way of telling that I should probably look at some material which is very soft, right? So which has a lot of polarization fluctuation. Then I can say that this material can be a good piezoelectric or can be a good capacitor or capacitor with large values of capacitance, right?
Okay,
If I
sir.
need an application where I need it to be piezoelectric, but I
Mhm.
don't really care about large values of piezoelectric coefficient, like, so I want to make a resonator, right? So
Mhm.
piezoelectric resonator. There
Mhm.
I want, my quality factor, what is called quality factor, to be as large as possible, right? But I
Okay.
don't really care about, how big this piezoelectric coefficient is. Then
Okay.
I want to reduce the losses, right? So I really don't want to enhance the D33 or the value of piezoelectric effect, but I
Mhm.
want to reduce the losses as much as possible,
Mhm.
right? As a result, we should not just look at equilibrium properties, we should look at the loss properties also, which is,
Mhm.
the third part of the course, where we said there are a lot of properties that give losses to the material, right?
So,
And then, yeah.
so Professor, now you're trying to come to the stage of the course where you're trying to optimize or get the performance at the best, let's say between the juncture between solid liquid phase. Is that the phase you're talking about, Professor?
Yeah. So now, so I was talking about phase transitions,
Okay.
right?
Hmm.
Because at the boundary of a solid and a liquid, let's say,
Yes, sir.
or at the boundary of these phases, typically, so something like density of water just is huge, right?
Hmm.
Because the density fluctuations are huge, right?
Hmm.
As a result, certain properties come because of these fluctuations, right? So at the boundary between a ferroelectric and a paraelectric phase, right? For example, the susceptibility becomes huge. Okay. So if I want if I really want to design a material that, so now I don't know which material it is, but I want to design a material. But the basic physics tells me that if I'm at the verge of some phase boundary, right, I can enhance the properties. Okay. So that's the physics of it.
So
Now, yeah.
enhancing, would you say, would you try to put some heterogeneous layers between to get that
Right.
Okay.
So how can I really enhance properties? But again, that goes back to what you're saying. So if I have just one material, that one material will have one phase transition temperature. So the properties are huge at 360 degrees Celsius. Let's say that is randomly the phase transition temperature, right? But I want this material not just to have a very high, susceptibility or piezoelectric coefficient at 360 degrees Celsius, but I want it to be stable over temperature, from room temperature to all the way up to high temperature, or even lower temperatures, right?
Yes, sir.
Then the question is, okay, then instead of just building one material, right? What about if I assemble several such materials together with slightly differing, phase transition temperatures? Then, so I'll have an average property, which is huge because some material will be at its phase transition temperature, right? So this is the curve where I have several layers, right? So that's what you're saying, which have different phase transition temperatures, right? So then that's one way of designing, a heterostructure, as we say, right? So I can make thin films which are slightly different in composition, but which have this phase transition temperature which spreads over a certain temperature range, right? So then I have made my material which has a large, piezoelectric coefficient over a range of temperatures. However, the issue is also going to be stability, right? So if I put if I start, putting heterostructures, let's say one of them has more zirconium, the second layer has slightly less zirconium, the third layer has even less zirconium, just for example. Okay. Then once I start applying an electric field, or once I start thermally cycling it, right? So diffusion will take place, right? So atoms are, mass would like to move from high concentration to low concentration. There's always going to be low, this diffusion that happens. Okay. So as a result, the material that you made is not exactly the material that you end up with eventually, right? So the cyclabilities and other reliability issues you'll get, right? So as a result, then we have to solve that issue. That's the engineering problem. So then I said, okay, why don't we just put some layer which is a diffusion barrier, right, in between these layers, and that way I'm solving the issue of diffusion that can happen. Okay, so this is something that I, so this is how you design. This is the engineering of materials, as we say, right? And then I also have the physics embedded in it, that different layers have different transition temperatures. So overall, I'm going to get an average susceptibility, or so that is that is large over a range of temperatures, right? So that's sort of, the design principles that I'll use to build this material that has large susceptibility or large piezoelectric coefficient over a large range of temperatures. Okay, so I mean, that's why, so at the end I don't make the connects every time. But so if you know the principles, when the time comes, right, so when you have to design some materials, the idea is that you will be able to do it yourself.
Okay, Professor. So, Professor, towards the end, you spoke about relaxation, resonance, diffusion. I think that was going more on the atomic and the ionic state. Any reason? I know that's the basic that starts off. Any reason or specific that you would want to uh, point out here, Professor?
So I mean, again, the thing is, okay, so you see, so all these properties, right? So I speak about these properties as if, one property is sacrosanct for a material. If for I give you this example of hafnium dioxide. Hafnium dioxide has a dielectric constant of something like 20 or 25 under, low frequencies, at frequencies where I measure. But if I see the same hafnium dioxide and measure it in visible frequencies, it has a dielectric constant of 3 or 4, right?
Okay.
So what I thought was a very sacrosanct property that determines what the material is, right, is not actually sacrosanct. It really depends on at what frequency am I measuring, right?
True.
So all these so then, so if I do a gigahertz experiment versus say I do a visible light experiment, I should be aware that my material itself can change its property, right? So as a result, so then we see what is the physics of it. So all these properties have come from atomistic dynamics. So the first part we said, okay, properties are related to the structure. That is structure property correlation, right? Structure and symmetry are sort of static entities, right? So I say that, okay, my aluminum nitride has a Woodside structure, right? So atoms are placed in these positions, and and that is what gives me some polar axis, and that's what gives me these sort of properties, right? So I did a structure property correlation. But in reality, so all these atoms are jiggling around, wiggling around. There's a lot of dynamics to these atoms, right? So not just at an atomic scale, but at different scale, there is a lot of dynamics. And ideally, what happens is these dynamics are what determines the properties of the materials. It's not simply the structure. Structure is correlated to the properties. That's why you say structure property correlation. But the dynamics determine the property, right? So at the end, we actually look at the dynamics. We say all properties are frequency dependent. Okay, so we start with that assumption. And then we say that, okay, so why are they frequency dependent? Because certain phenomena such as polarizations, right? So if I have ionic polarizations, for example, ionic polarizations are only active below terahertz, right? So above terahertz, they are not active. So above terahertz, I have only so the electronic polarizabilities that respond to external electric field, right? So the material behaves completely differently above terahertz and below terahertz. And when you're actually moving from below terahertz to above terahertz, there are these phenomena of resonances and relaxations that happen, right? So we sort of build a physical model to actually understand that. Okay.
Yeah.
And this sort of trying to see the dynamics of properties, right? So for example, if I look at conductivity, right? So conductivity means electrons are flowing, or so some sort of charged particle is flowing. If I look at capacitance or capacitive currents, it's the same charged particle, but it is not flowing in the sense that I have a flux and force. But I have some sort of if I I have what is called a displacement current, right? So this charged particle is following the phase of the voltage, right? But the dynamics seem to be coming from same origin, right? It's a similar charged particles at least, right?
Yeah.
So all this analysis that we do eventually, if you put in the idea of causality, will tell us that these are actually related. It's the same, so whether I measure conductivity or whether I measure capacitance, right? They are actually, the same or different sides of the same coin in some sense. So they tend to be related, right? If my material is lossy, so that will reflect in the equilibrium, corresponding equilibrium property. If my material has a large conductivity, that will reflect in the capacitance measurement.
Sure.
Right. So and so on and so forth. So the losses are related to the fluctuations. One is related to fluctuation, the other one is related to loss, right? So so it's not that, yeah. So these are not some independent properties. The dissipative properties and equilibrium properties, they are related. That's how we end the course, right?
Okay.
And then say, so tomorrow, if someone says, okay, my PZT, so typically this is an observation, an experimental observation. I'll just give you right now.
Yes, sir.
So if I have a material, again, we'll go back to piezoelectrics, right? If I have a material that has a high dielectric constant or high piezoelectric coefficient, it typically has a large piezoelectric loss, right? So if I want a less lossy material, like I said, for resonator applications, I want to choose a material that has not so much loss, right? So I don't really care about the value of the piezoelectric coefficient. There should be some piezoelectricity, but it should not have so much loss, right? Then I tend to actually sacrifice a lot of the piezoelectric coefficient, which is the real part of D33 in that sense, right? So or the equilibrium part of D33. Yes. And then I tend to take, a material such as aluminum nitride, which has low loss, but low piezoelectric coefficient also. Okay. Typically, these tend to go together. If I have low loss, I have low real part. If the imaginary part is low, the real part is low. If the imaginary part is high, the real part is high. Yeah. Okay. I mean, what relates them? One is loss, one is, an equilibrium property, right? So that's where the fluctuations and dissipations come. If I have a lot of fluctuations, that also means that I have a lot of dissipation, right? So that's the last part of the course. So that also gives me a design principle. Can I use PZT to make a resonator? Probably not, because it will be very lossy resonator. You'll have a pathetic quality factor and so on. But can I use aluminum nitride to build a microphone? Probably not, because there I don't care about loss. The microphone can lose a lot of the transduction doesn't need to be 100% efficient. I don't need a 100, so a very good quality factor for my electromechanical transduction, right?
Yes,
And so I'll use PZT for that application. I'll use aluminum nitride for this application, right?
Yeah.
So you'll not get everything for free. If I'm sacrificing on the loss, I should also sacrifice on the real part, right? So that's sort of a intuition we should be able to develop. Okay.
Yes, sir.
Yeah.
Thank you, Professor.
Okay, Sanjay, thank you. So there are, I think Vishal is here, but there is someone with an iPad also. I don't know what your name is. Vishal, maybe we can start with you if you have a question. Vishal, can you hear me? Okay, iPad person. Okay, Vishal seems to have unmuted.
Yes, sir. No questions as of now, sir.
Okay, Vishal, where are you from?
I am from NIT Surathkal, sir. Final year
Okay,
BTech student from Metallurgical Department.
wonderful. All right, good. So the person whose name says iPad, can you ask? I mean, if you have some questions, can you ask? You can also type if there is something. Oh, okay, it's Anudeep on iPad. Fine. So Anudeep is our TA. Okay. I saw someone else joining, but maybe that person left. Okay. So are there any more questions in general? Sanjay, Vishal, if there are none, we'll end this session, but always feel free to email me, right?
Professor, one last question. Of course, this will be more related to the. I'm also writing the examination, which is coming on the somewhere in the beginning of the month, next month. Any insight what we should be focusing
Studying.
to? Yes, I know I shouldn't be asking this question, but then yeah.
No, why not? So I think mostly it's going to be multiple choice, right? And so various things that were discussed in class essentially. So an example question, I don't know if this is a question that we give, but an example question is something like, okay, something about just blanking. Okay, so if I have, let's say, 4-bar symmetry, what is the underlying polyhedron that I can think of, right? So is it a tetrahedron? Is it an octahedron? Those sort of questions, right? So mostly course, I mean, so classroom related, right? So I think very little of problem solving and things like that. But so if you look at the class notes a bit well, you should be able to do it quite well. Okay. And all of them are multiple choice questions. So and then so the TAs actually made the question paper, so you can actually ask them also. So there are so can you identify symmetry? So we'll give you some shape, and then you should be able to identify if there's a mirror plane there, if there is some twofold axis of rotation. That's from the symmetry part, right? Then from the later part, okay, so what spectroscopic tool will you use to identify let's say some phenomena happening at 100 or 50 milli electron volts, some vibration loss, that is, or so some vibrational states that are separated by 50 milli electron volts. So what are the spectroscopic tools that you may use? So Raman, for example, does that, right? So that will be in the last part. Okay. But before that, if I'm thinking, so what is Seebeck effect, for example, right? So and then you apply temperature gradient, you get voltage, or you apply voltage, you get temperature gradient, or you apply temperature, you get voltage, right? So we'll give several such options, and then you should be able to pick the correct one. Okay.
Thank you. Of course, Professor, you also spoke about in one of your sessions an IC interview question also. I like that question. So
which was the question? Sorry,
I don't remember, but then I think it was in session week 10 sometime.
I see.
One
Okay.
example about an very frequently asked question for an IC interview for anybody who is inspiring to get to do research or something.
Wonderful. So yes, I'm outing the question papers.
Yeah, you're kind of motivating us in all aspect. Thanks again, Professor. And yeah, this was a nice course. I'm looking forward the last week of the course, maybe
Sure,
closing
sure,
and trying to get the real insight of it. Thank you,
sure, sure, sure. So glad that you liked it.
Professor. I kind of really understand it now. Work
Okay,
for
good.
further on it and see what can I do.
Right. Okay, no problem. Okay. All right. So we can then conclude. But if there are questions, always feel free to email me. Yeah. And also
Sure.
on the NPTEL portal, I think even if I don't respond, we have a set of very dedicated TAs here, Anudeep, Shomo, and Shubham. They are always on it, trying to answer questions and yeah.
Okay, sir. Then shall I end the session?
Okay, let's end the session. Yeah.
Okay, sir. I'll make M for everyone. Thank you, sir.
Okay. Bye.
Thank you, sir.
Professor.
Bye.
Bye.
Yeah. Bye.